Поехали.
Welcome everybody to Integrability Journal Club. And today I'm very glad to introduce Gustavo Joaquin Turiaci from Santa Barbara, who will tell us about 2D dilaton-gravity and matrix models. Please, Joaquin.
Okay. Hello, everyone. Thank you very much for the invitation. Yes, I will be talking about this, and feel free to interrupt me at any time if you have any questions. Okay, so I will start. Okay, the talk will have 3 parts. Hopefully, part 1 and 2 will be the first 40 minutes. That I understand there is a break afterwards. And I'm going to quickly review Jackiw-Teitelboim Gravity and the relation to matrix integrals. Then in the second part, I'm going to, so this is based on this paper of Sachin and Stanford, and then in the second part, I'm going to explain a generalization of this to any arbitrary 2-dimensional dilaton gravity. We worked out in a paper with Maxfield, and also some independent work by Witten last June, July. And then in the last part, I will explain in some detail the connection between these theories of 2D gravity and the non-critical minimal string, and use it to get some new results. And this is based in some paper we wrote with Thomas Mertens, and also some paper from November with 2 students here, Michel Zetiuk and Wayne. Okay, so we'll start. So what is Jackiw-Teitelboim gravity? So it's a simple 2-dimensional theory of dilaton gravity. It has 3 terms. The first one is topological, comes with some coefficient S0, and will be important later to weight when we will sum over topology. So this will give us a weighting in the genus, but for now it's just a coefficient. Then we have the KT term, which is linear in the dilaton, proportional to R+2, which will be important. And then we have the last term, which are the Gibbon-Hawking terms, York terms, which I didn't write down, but they are very important to get the right dynamics of the problem. So first question is, okay, so we want to study this theory of gravity in asymptotically ADS space and try to study holography, what holography means in this context. So first we need to decide what are the boundary conditions. And the boundary conditions is that we will fix, so this is 2 dimensions. So we have radial direction and time, which is the angle. So this is Euclidean space. And we will fix the length of the boundary to be some very large number, and we will fix the dilaton to have some very large fixed value in the boundary. And the point of this parameter epsilon that we will take to 0 is that we want the ratio to be fixed. So this is just the definition of the boundary conditions. They both diverge, phi and L, but with a fixed ratio. And this ratio is what we call, this beta is what we call the renormalized length, which is the inverse temperature of the quantum mechanical system that would live in the boundary. And gamma is some dimension full scale that we could set to 1 by some change of coordinates, and I will set it to 1 later, as by fixing the scale. Okay, so this theory is very easy to solve, and it's important that this is linear in the dilaton, and the idea is to first integrate out the dilaton. Now this imposes that the metric is hyperbolic, so this imposes that the path integral over the matrix collapses to integrals over metrics that satisfy R+2 = 0. So in the case of the disk, so this is, usually imagine this as a Euclidean black hole, so there is some horizon in the center. And in the case of the disk, there is only 1 metric. So, okay, that's just the hyperbolic disk. When we look at higher genus corrections, there will be moduli spaces of metrics, but for now it's just 1. When you do this, the theory reduces to a boundary mode because you only sum. So the only degree of freedom that appears is how you cut a patch of this hyperbolic disk in a way consistent with the boundary conditions. And if you look at this in detail, and that's the point of all these papers, couple of years ago. There is one function worth of boundary curves, and this you have to integrate over them, and this gives you the Schwarzschild mode. So there is some action you can write, and it comes purely from the boundary term. Okay, and that way you can do the path integral, the complete path integral of Jackiw-Gravity in this topology. Before I mention the result, let me say that the physics of this mode is controlled by the broken conformal symmetry of the problem. So if you had anti-de Sitter, two-dimensional anti-de Sitter space, you think you would have a conformal symmetry, which are the isometries of ADS2. But this a limit where that symmetry is preserved is pathological for several reasons, and that was a cause of confusion about ADS2 holography for a long time. And the resolution, or the nice thing about this mode, is that this breaks this conformal symmetry and it makes the problem well defined. And that is because when we integrate out over this dilaton can fluctuate. So there is a background for this dilaton that breaks the symmetries of ADS2. So that's important. And this gamma you can think of as the scale at which the symmetries are broken. The conformal symmetry is broken. Okay. Okay, so you reduce the theory to this boundary mode, and then it can be exactly solved. I'm not going to write it because it would take me too much time, but the upshot is that you can write the path integral exactly, and this is the formula. So it depends on this scale gamma and the inverse temperature. This exponential is the classical term. So this is the classical action. There is a classical solution to the problem, and that's what it is. And this prefactor is like a one loop determinant that happens to be exact for the partition function, which is the content of this paper, the fact that this is one loop exact. And then in this paper, we solve for any correlator you might want if you add matter, but that's not what I will do. And this e to the s naught is, you should imagine, as a very large number that comes from the topological term. From this density of states, from this partition function, you can extract the density of states. That is this sinh square root E formula, and it has this shape. So at large energies, it grows exponentially, consistent with the semi-classical limit, and at low energies, goes to 0 as a square root E. So that should remind you already of some matrix integral, maybe, that might be describing this problem. But okay, that will be next. But before I move on, let me mention, so we will sum over topology. So why do we need to do that? And the problem is that this spectrum is continuous. So there is something called the spectral form factor, which you can think of basically as a pure gravity version of the two-point function. And this decays in time forever. And in holography, we know that if the system is dual to a finite, to a holographic theory with a finite entropy, then this cannot decay forever. At some point, there should be something going on, and there should be fluctuations of the size of exponentially small in the entropy, but finite. So even though this system can be exactly solved, it has some issues so that we would like to resolve. And the proposal of Sachenko and Stanford is to sum over topologies, and we will see how this resolves some aspects of this problem. Okay, so we'll sum over topologies. We want to do the path integral with this. So for generality, we will allow any number of boundaries with some renormalized length beta 1 to beta n. And we will do the path integral over all geometries that fill this up. So what are the steps? So we are going to do this path integral exactly, and that is what Sachenko and Stanford did. And so I will give you now a summary of the steps. So first, we have this number of boundaries, and it's useful to focus on a contribution at fixed genus, G. And the reason is that we can expand this path integral as a sum over, so you can think of e to the minus s naught as a sort of string coupling in a way, where it's weighting higher genus contribution in some way. So the next step is to compute this quantity set Gn with a fixed number of boundaries at fixed genus. So the first step is we integrate out the dilaton again. So we have to integrate the metric collapses to an integral over hyperbolic surfaces. So this is an example with 3 boundaries and 3 handles, where this is supposed to be hyperbolic metric, but don't take it too seriously, the picture. So the next step is to, we will identify geodesics that are homologous to the boundaries of length B1, B2, and B3. And we are going to separate the geometry in this way and compute the contribution from each component. So we have these so-called trumpets, which are the things that glue the geodesics to the, let's say, I would call holographic boundaries, where by holographic boundaries, I mean with the proper boundary conditions. And then we have this bulk term with geodesic boundaries. And the nice thing about this is that there is no boundary mode here. So the only contribution from this is basically you just have to count the number of hyperbolic surfaces, and that's the way to count it will be to compute the Val-Peterson volumes. Well, of course, it's a moduli space, but it's just okay. And then the last step will be to glue everything together. And so, as I said, the contributions from this region will be the Val-Peterson volume, and we will glue with the Val-Peterson measure. So you could say that this theory is three level exact because there is no one loop. The one loop corrections are trivial, and that's why we only consider these volumes. Okay. So the ingredients are the path integrals in these trumpets and surface with geodesic boundaries. You can do the path integral in these trumpets in the same way as we did for the disk. But now this Schwarzschild mode that lives in the boundary, so that's this red line here. This theory will depend on B, where B is the length of this geodesic boundary. So you can write the theory, you can exactly solve it in the same way as we did for the disk. And this is the answer. So it depends on beta, which is the renormalized length of the holographic boundary. It depends on B, the length of the geodesic. Yeah, and it doesn't have any factor of S naught because it's like topologically an annulus, so Euler characteristic 0.
Can I reproduce disk topology if send B to 0?
Disk topology. No, that's the...
Yeah, because the answer looks different from previous one, yes.
Yeah, so the limit B to 0 is more like having actually I will mention that later maybe, but it's like a disk with a puncture.
Yes, with a puncture. Okay.
And yeah, okay. Yeah.
Can I also ask some basic questions actually about previous steps? So B, you have integration over B's, yes? So B, it is only one parameter which parameterizes trumpets?
No, sorry. There is another parameter which is the twist. So when we glue these two geodesics, you can do you can rotate the boundary a little bit or any amount before you glue them. So yeah, you also have the twist, but the nice thing is that everything is independent of the twist. So it's kind of easy to take care of that. Yeah. So those are the two parameters.
Yeah, and another question also about definition just of the measure, so of your functional integral. So in principle, you have a lot of restrictions on metrics. Yes, you have boundary condition, it should be R equal -2, and it's certain topology. So, and you tell us that, okay, actually this space is very narrow. It is parameterized by a set of these B's, and Peter in this volume on modulus of Riemann surfaces, yes?
Yeah.
Okay.
And something non-trivial is that.
So, for example, why you choose this metric exactly as this metric on the moduli space? Maybe it's a very naive question, but okay, you have some functional integral over metric. Yes.
Yes.
So, and then you write some particular formula. Why exactly this you use this measure for this?
That's maybe what I meant by three-level exact. So you can derive the measure from the original path integral over matrix.
Okay.
So the fact that you integrate out the dilaton first. So if where is it? So imagine this sits in an exponential. So this gives you like a delta function of r+2.
Yes.
So you have an integral over matrix with a delta function of r+2. And then, oops, okay, so then you integrate over r+2, but then you have like a one loop factor that would tell you what is the right measure that you should pick when you integrate over hyperbolic surfaces. And this measure, the naive one would be the Weil-Peterson volume, and the statement that Jackiw-Gravity is 3-level exact just tells you that that's actually all you have. So there is no finite dependence. So yeah, I mentioned this because if you look at non-orientable surfaces, that was done in a paper by Stanford and Witten, then this 3-level, you lose this property. And now you have a one loop determinant that depends on B that you need to add on top of the Weil-Peterson measure when you glue and you do all this. So that's, yeah, there is a lot of, I'm just telling you the summary, but there is a lot of calculations.
Yeah, just to understand main steps. And if you integrate over moduli space, it means that conformal transformations factored out here. Yes.
Yes, and yeah, and also the mapping class group, which, yeah. So it's a moduli space. It's not like Teichmuller space or anything like that.
Yeah, moduli space of Riemann surfaces, it's exactly a factor of equivalence over conformal transformations, yes? Yeah, so it means that conformal transformations you factor out somehow in this passing.
Yeah. So, and yeah.
Sorry, Joaquin, maybe not everyone in this audience is familiar with these calculations. Say for the disk, you can just start from Liouville theory, yes. How would you just practically? How do you compute it? Let's say the disk partition function.
Yeah, so this is a little different than what you would do in usual 2D gravity, but yes, you can do the gauge fixing and you'll end up with some Liouville term. And they also study that in the Sachenko Stanford paper. But the Liouville term is kind of, it doesn't affect the answer. But maybe that's like another way of saying that this is 3-level exact in the sense that the one loop determinant is not.
One loop determinant of what? Of the metric?
Of the metric, yeah. When you want to collapse the integral over metrics to an integral over a subset of hyperbolic metrics, then you need to say what the measure, how the measure from the measure of integrals descends to the measure of the integral over hyperbolic metrics, modulo conformal transformations and all that.
Okay.
Yeah. Okay.
Maybe another basic question, kind of physical question. So disk topology corresponds to low energy SYK, right?
Yeah.
Yeah. So what in the language of SYK is this more general topology? It is some observable, so it is coupled SYKs. So when you have several boundaries, not just one disk boundary.
Yeah, so in that problem, I guess there's probably, well, it is harder to compute. So I don't know of a way to make it precise, the connection with SYK. Like I don't expect this to be a good approximation to, so in SYK, the disk is like in a large N. So then maybe this you have to look at effects that are exponentially small in N. And that's something that is beyond the reach of doing analytic stuff in SYK. So in the disk, you can derive the Schwarzschild from SYK, but I don't expect to be, or I don't know how to say anything concrete. These are very small corrections, that's what I'm trying to say. So at this point, you can forget about SYK. This was just a motivation from studying 2D gravity.
Okay.
Yeah. Is there any other question? I guess this is important. So yeah. Maybe just to mention what Vladimir was saying. So yeah, it's important that this theory is a little different from what you might have in mind from 2D gravity, because this is so simple that you have this linear dilaton that allows you to integrate over metrics in an easier way than usual. But okay. This is also related to Liouville gravity in a way that will be the topic of the last part. So maybe we can talk about that later too. Okay. Okay. Is there any other? Okay, I guess I should move on. Okay, so hopefully now we're on the same page about what this means. So the ingredients that we need is the partition function in the trumpets as a function of boundary length B. And yeah, I didn't mention it, but this is independent of the twist. So this path integral doesn't depend on the twist. Well, of course, the twist is something about how you glue. And the hyperbolic surfaces with geodesic boundaries. So I said this is like 3-level exact in a way. So this is just the Weil-Petersson volume. So what this VGN of B is just the volume of this moduli space with geodesic boundaries of fixed length with the usual Weil-Petersson volume measure. And these numbers were computed. A way to compute these numbers was developed by Mirzakhani, and I'm not going to write it down because it's kind of a mess, but there is a topological recursion. There is a recursion relation that these volumes satisfy, such that if you know the answer for some simple cases, you can plug it in your recursion and find them all if you want to. So in principle, we have everything we need to solve the theory. And this is an example of what the final answer would look like. So we have this Weil-Petersson volume here. Depending on the B, we have these trumpets, one for each boundary. We multiply. And then when we integrate over B, we have dB, and then we have these factors of B. So the measure is BdB. And the origin of this factor of B is because of this integral over twist that I didn't I didn't write down in detail, but hopefully you can imagine. And the reason why this is B is because before you glue the boundaries, you can rotate them, but at most a distance B, because that's, if you go around full circle, then the twisting is trivial. So that's why this is some finite factor of B. Yeah. Okay, so this way you can compute all the coefficients set Gn that appears. So if you can compute exactly any quantity you want of this pure gravity theory. Okay. Okay, so Sachenko and Stanford, besides solving the theory, realized that it's equivalent to a matrix integral. So the idea is, so on the left-hand side here, we have the gravitational calculation I just described. And on the right-hand side, we have an integral over a matrix H that is size L by L, where L is a parameter that depends on S naught. So these corrections that are exponentially suppressed in S naught are really like the Toft expansion of this large matrix. And here the reason why this is a wiggly line is because this is in the double scaling limit. So okay, you have to be careful about how you describe this. So you have this integral over matrix, you have this probability distribution, and then you have, for each boundary of renormalized length beta, you insert this quantum mechanical partition function, trace of e to the minus beta h. So this tells you that h should be interpreted as a Hamiltonian of the boundary theory. So you have asymptotically ADS2, we expect some theory to live on the boundary, it should be quantum mechanics. And the surprising feature is that it's not a single quantum mechanical system, but it's an average over them. And okay, and this probability distribution has the form of the usual matrix integrals in terms of a matrix potential V of H. This is hopefully familiar. And this function V of H, this matrix potential, is completely specified in terms of what the leading order disk density of states should be. So once I tell you that to leading order in large L or large S naught, you should get this sinh of square root E that I wrote before, then that determines this V of H, well, up to some subtleties, but about the double scaling limit.
Can I ask you, Sorry, maybe Zhenya first.
No. Well, I had a very short question. If n equal 1, it means that SYK is equivalent to some matrix model, yes? If n equal 1.
If n equals 1 and you take large S naught and you keep only the disk. So SYK is not a matrix integral, but it's something like a matrix integral in the sense that you can think of it as an average over theories, but this probability distribution over Hamiltonians does not have this simple form. It's very complicated.
Yeah.
Which is described through, well, integrating over the couplings and all that. But again, the things exponentially suppressed in S naught, I don't know how to relate them to SYK. Thanks.
So the question, another question. So you mentioned that the interpretation is that the theory is dual to an ensemble of quantum mechanical models. But here, so naively, it seems that the H is just a finite matrix. So this trace of E minus beta H is, it's not clear why it can be interpreted as quantum mechanics partition function. It's just a finite matrix. And in quantum mechanics, we would expect it all to depend on time or something like that, to have some continuous degree of freedom or dependence.
Yeah, maybe what bothers you. Yeah, maybe what bothers you is that I'm not writing the Hamiltonian as like an integral over time, or I don't have like
there is no time apparently.
No, there is time because you have beta, right? But the point is, any quantum mechanical system, if you have a time independent Hamiltonian, the partition function will have this form where H is a matrix. Like that's true about SYK, for example. Maybe what you don't have here is a description in terms of fermions that tells you how to write the matrix in some. You don't have a notion of the degrees of freedom that make them. You're just integrating over Hamiltonians. But I don't know, if I tell you the Hilbert space and the matrix and tell you that it's a Hamiltonian, then that specifies the theory as much as.
Yeah, but should we think that L is going to be large or it is just finite?
L is large. Yeah.
Oh, okay, then it makes kind of more sense to me.
Yeah, so it's like some very big matrix that. But yeah, so what I was saying about SYK, so SYK you could describe as a Hamiltonian with the fermions, like telling you that the Hamiltonian is the sum of like some coupling, some fermions to some power. But I could also just write a basis of that Hilbert space and just compute the entries of the matrix and just give you the matrix with a lot of zeros and ones and things like that.
Right. Yes.
So this is more like that. Yeah. And this is related to the fact that we have pure gravity, maybe, because if we had matter, then maybe we had some observable in the boundary that is not trivial that could tell you more structure about the theory than just the Hamiltonian. So yeah, so this might be related to the fact that it's pure gravity only. It's so simple. Yeah. Okay. And okay, yeah, so before I move on, and so this equality here can be shown order by order in this large S naught expansion. The idea, yeah, I'm not going to write it down, but there is a recursion relation that the volumes, that the Weil-Peterson volumes satisfy, derived by Mirzakhani, and that allows you to derive a recursion that the partition function at fixed genus satisfy, and that's exactly the same as the loop equations of the matrix integral. So that's order by order. You can show that they match, and that's what the SSS did. Okay, so this is a summary. So okay, this expansion in genus makes sense both in gravity and in the matrix integral. Of course, in the matrix integral, it's just the top expansion in the double scaling limit. Okay, yeah, that's what I said already. It's like a summary. So the density of states in the disk fix it completely. Here we have the volumes. And the quality of these two things was proven by Einard and Orantin, the fact that they both give the same answer. And this is, okay, the interpretation I just mentioned. Okay. So let me mention briefly, so we have this something called the factorization puzzle. So we have these cases of holography. gravity in ADS being dual to an ensemble of theories and not just a single theory. That's difficult to see, but there is a smoking gun for this holography with disorder. There is to compute the path integral with two disconnected boundaries. And as long as you can have these wormholes or these geometries that connect them, where this is a space-time wormhole, so this is Euclidean time. This is not this is not an Einstein-Rosen bridge. Then the path integral with these two boundaries is not equal to the product. So if your theory would be dual to a single quantum mechanical model, then this would be an equality, right? Because these are completely independent. You just compute the partition function of each and multiply it. But the presence of these wormholes tells you that this is different. So that's this is an interesting quantity to study in general. Maybe in a case where you cannot study the full duality and you cannot prove it exactly, at least you can analyze these geometries to see if it's dual to a theory with disorder or not. And maybe I will skip some extra comments. Okay. Is there any question before I move to the generalization of this? This idea of the matrix integral is important, so if there is any question, let me know. Okay. Okay, so now I will briefly explain a generalization of Jackiw-Gravity by adding a class of defects. There are two motivations to do this, and one is that we want to generalize the dual matrix integral to general dilaton-gravity theories. So the idea is that there is one function worth of matrix integrals given by the matrix potential. There is one function worth of dilaton gravities given by something called the dilaton potential. So it's natural to expect them both to be the same, and that's what we want to see.
So, sorry, can I ask a question? Yes. Yeah. So these relations about topological recursions, etc. So it is already about double-scaled matrix model.
Yeah.
Yeah. So and what exactly is the double scaling here? So somehow you showed us just this.
Yeah, the double scaling just means that this density of states to leading order goes all the way to infinity. Which, if you have a matrix integral that is not in the double scaling limit, you usually have some finite range of the eigenvalues.
Yes.
So double scaling limit means just that here this is cut off somewhere at the finite energy, and I'm taking that cutoff to infinity.
Mm-hmm.
That's the only thing I mean, yeah. So the relation between L and S naught depends on the precise relation depends on how you cut it off.
Yes. So it is going inside of this. So I want to ask actually about connection to double scaling in ordinary matrix models. So in that case, the role of double scaling is provide some regularization, some sense to the continuous limit, yes, of discretizations, etc. So here, how would you describe?
Yeah, that's for me an open question that I would like to understand better, which is well, yeah, I was going to mention this when I talk about the non-critical string because maybe it's more familiar there. This idea of the surfaces of this matrix as a triangulation or something like that on these surfaces.
Mm-hmm.
And this gives a different perspective on the matrix, so that's why that's something interesting about this Sachenker-Stanford result. And I don't know how to relate the two notions of the matrix in a precise way. Yeah.
I see.
They give the same answer, of course, but yeah.
But at least this topologies, we can think about this topologies as world-sheet topologies.
Yeah. And I will tell you the string, non-critical string that reproduces all this.
Okay, good.
So yeah, so it gives a new twist, if you want, on this old matrix model dualities from the 80s and 90s, where no one would have called it, I guess, I don't know, in the 80s, this matrix Hamiltonian of some dual theories. Yeah.
So just quick question, can you remind what actually is the probability distribution? What is it equal to?
It's literally this, and so
what
to
is
find
V
a matrix.
of H?
Huh?
What is V of H?
Yeah, so this is the matrix potential, well, it's just a name, but in matrix integrals, you usually put you put factors of this form because they're easy to compute. V of h is the matrix potential. It's a function of the matrix, and this V of h you can find. So if you tell me in the disk what is the density of states at large L here, then this, which is this, okay, this function here. So there is this specific function. Knowing this determines the V of h completely.
Okay,
Or,
I see.
well, completely up to the double scaling limit. I mean, let's say you regularize the double scaling limit, then you compute V of h, and then you take the double scaling limit. Yeah. Yes. And the amazing thing is that this path integral of Jackiw-Gravity is the same as the input that you need for the Mirzakhani recursion of the volumes. That was in this paper from this. Okay. Okay, I will move on if there's another question. Okay. So I was mentioning that I will be interested in Jackiw-Gravity with defects. So
sorry,
yes.
One more question. These numbers which you say, say Mirzakhani has derived, they also, I think they were already observed, at least, I don't know, maybe not all of them calculated, in the topological two-dimensional gravity, yes?
Yeah, that's true. Yeah, you're right. Okay, sorry. Yeah, maybe I should have mentioned that. Yeah, I guess. Well, in the two-dimensional, well, the point is that when you compute these volumes as a function of the length of the boundary here, these are finite polynomials in the B, in the length, and the coefficient of these polynomials are the intersection numbers of two
intersection numbers, exactly.
Yeah, so you can construct this object with those techniques. Yeah.
What was the, I mean, the achievement of Mirzakhani? She really gave practical recursion relations to compute them. Was it not? I forgot. Was it known how to compute these intersection numbers?
Yes, I don't think before. I think she introduced. Well, I don't know. I don't want to say something wrong, but I think before people didn't talk about surfaces with these geodesic boundaries. And I think she derived a recursion relation that allows you to compute them, which wasn't like people only were able to compute some particular cases. And then she showed that these coefficients are related to the intersection numbers. I don't know if that was obvious or not before her paper. But
so she related it with to these Wild-Peterson volumes, etc. Yes.
Yeah, I don't know. At least her paper makes the relation very clear, and but yeah, I don't want to say something wrong because I'm not super familiar with the literature from the 90s. So
I also forgot all this.
Yeah, but I mean, of course, the main point about this is that her recursion relation is exactly the loop equations of the matrix integral. So that's the natural way to try to connect it.
Yes.
Yeah, there are some papers, I don't remember the authors, of people that try to make the connection through the intersection numbers and this other approach to 2D gravity, but yeah. Okay. Okay. So, yeah. Okay. If there is another question, I will continue. So adding these defects. So okay. Sorry. Yeah, I was saying. So we will do Jackiw-Gravity with a gas of defects. And what I mean by this is that we will allow some singularities in the geometry described by conical defects with a deficit angle theta. Now, for technical reasons, it's more convenient to label them by alpha, and this is how they are related. So, alpha equals 0 corresponds to a cusp So the deficit angle is 2 pi, and alpha equals 1 corresponds to no defect. So the deficit angle is 0. And this parameter lambda, that I will call the fugacity, is a parameter that weights the contribution from how many number of defects you have. So if you add n defects to the geometry, they will come with a factor of lambda to the n, for example. So it's like a fugacity of the, and we will sum over the number of defects. So we are not going to restrict to any fixed number. And that's the theory we want to consider. Jackiw-Teitelboim with a class of defects.
So in the vicinity of this defect, of this singularity, you can still have r equal -2 curvature surface. Even in the vicinity of this defect, it is...
Yeah, you have, well, the surface will be r+2 equals sum of delta functions at the defects.
Ah, okay.
Yeah. So we are by hand allowing some singularities and summing over all the positions with some rules. And the point of why we want to do this is that adding one defect, and maybe this will make your question clear, adding one defect is equivalent to inserting this operator in the path integral. And that's something we studied in this paper. And if you remember before, in the action, you have phi times r+2. So if you add this operator and think of this term only, this will give you the delta functions at the location of the defect that I was just mentioning. So if you add this factor and you integrate over the dilaton, then you will replace integrate over hyperbolic surfaces by integrate over hyperbolic surfaces with cone points. And if I sum over the number of any number of defects, then the effect is to just exponentiate this. And sorry, here I have an integral over the position. What this integral means is that I integrate over all the possible positions of the defects. So I integrate over the positions where the defect could be, and I integrate over the number of them. And then this gets exponentiated, and the net effect is to replace Jackiw-gravity by this general pure 2D gravity theory with this phi r plus u of phi. And u of phi is the dilaton potential, which is, this is the JT term, and these are the new terms which are exponentially suppressed in phi. And these lambda are the fugacities, and alpha is the angles. And I sum over I because I could have any number of species of defect, not only, yeah. I think I'm doing terrible with that. Hopefully it's okay.
Well, actually, we are more or less in the point of coffee break. So if you will find the point to pause in the next few minutes, will be...
Okay. Okay, I will go very fast over this then. Okay, so this covers...
Sorry, can I ask a question?
Yeah, sure.
This action which you get with the potential U looks perfectly smooth, and it's not clear why solutions should have any defects.
No, the defect only appears when you, so this is sitting in an exponential in the path integral, and the defect only appears when you Taylor expand in lambda. Yeah, so in a sense, the idea is that you add these defects and somehow a condensation of the defects or whatever is equivalent to shifting this dilaton potential. So in the end, you will have something smooth again.
But even if I add this, well, the original, well, written on the first line, the integral.
Yeah.
So yeah, then indeed it looks like a shift of the curvature, yeah, because
yeah, but by a delta function, because this is, so this phi is located at the fixed position that here we are integrating over, but before we do this integral, this will give you a delta function with this weight at the position of this insertion.
So effectively, it means that averaging cover all positions, smooth them out, all singularities, removes them.
I didn't. Yeah.
Well, averaging other positions of singularities effectively removes them.
Yeah,
Well,
something like that. Or it's equivalent. In the end, you end up with a theory that is with a smooth geometry, if you want, described by this new dilaton potential.
okay, thanks. Yeah.
Mm-hmm. Okay. Well, okay, I will try to go fast. So if the deficit angle is not too big, if alpha is more than 1/2, then we can do the same cutting and gluing that we did before, but these Weil-Petersson volumes will be replaced by the Weil-Petersson volumes with cone points for the same reason. And they can be computed by analytic continuation. So basically we replace the defects by geodesic boundaries of length b, and then we replace b by 2 pi I alpha. And this is explained in these papers that's equivalent to the volume over cone points. And alpha smaller than 1/2 is important because I mentioned that we need geodesics to cut and glue. But if alpha is bigger than 1/2, or if the defect is not too sharp, then there might not be any geodesic in the geometry. And then the recipe of cutting and gluing cannot be applied. And we will use a different method, maybe later if I have time, to do the path integral in these geometries. Okay, so the general answer looks similar to before. We have a sum over genus with these weights, and now we have a sum over the number of defects. And we have this family of species, 1, 2, 3, etc. Each of them comes with a weighting of lambda to the k, where k is the number of defects of species I. And now instead of ZGN, we have ZGNK that depends on fixed genus, fixed number of boundaries, and fixed number of defects. And we need to sum over all of them, like I show in this picture. So this is sum over defects at fixed genus in the rows, and the columns are fixed number of defects, sum over handles. Now this sum can be done exactly because there is a formula that we derive with Thomas Mertens for the Weil-Petersson volumes on the sphere. Sorry, if we focus in genus 0, so before we include higher topologies, and that's important because we want to know what the density of states of the disk is, because that's going to be the input of the matrix model. That's going to determine the matrix potential. So that's something that we need to know if we want to make a connection with random matrices. So at genus 0, we can write this exact formula for the Weil-Petersson volumes. Maybe ignore the details, but it's in terms of a function u of x, which is defined implicitly in this way. And then this is for the case with boundaries, and for defects, we can do this analytic continuation. And okay, so when you sum over defects in the disk, you get this formula. So it's explicit, but it's a little ugly, but it is what it is. Is this integral over this parameter u, but it depends on the energy and the parameters of the defects lambda and alpha. And it depends on E naught. So when you add the defects, you have a shift of the ground state energy, if you want. And this E naught is given implicitly by this relation. Yeah. And here you can check if you put lambda equals 0, then you will get Jackiw-Gravity and everything will be the same as before. This is a picture of how it looks like. So you can see that it's just a smooth answer, but it's just a shift of the extremality of the, of the ground state energy. But something interesting is that if these fugacities or these couplings are too big, then you can have non-unitary spectrums, and we don't really understand why this happens. But for most values of lambda, this is a perfectly well-defined theory. Okay, we can actually compute analytically all amplitudes at genus 0, and we get this answer. This is in terms of this function u of x defined explicitly in this way. And okay, this is the answer. This is the exact answer for a Hermitian matrix integral in the double scaling limit for genus 0 amplitudes. Okay, I'm going to,
maybe. So what about coffee break? So can we?
Yeah. Okay. Yeah. Sure.
Now it's okay.
Yeah. Now it's okay. Yeah.
Okay. Good. Then then we'll call. Yeah.
Ready?
Yeah.
Okay. Okay. So now I will. Okay. So there were some things that I didn't have time to say, but let me just say the main upshot of what I was saying before is just that JT-gravity with defects is still a matrix integral. So I mentioned some calculations at genus 0, but you can extend them at any genus. And you have these quantities, and now these quantities ZGN in JT with defects you get from summing over defects. In the matrix integral, you get from the topological recursion applied to this new density of states. And there is a theorem also that guarantees that these two things give the same answer. So, okay, I went over this a little fast, but that's the main conclusion of this part. So for each dilaton potential, you have a matrix integral with a matrix potential that is dual to this theory of gravity. But okay, so now I will mention, in the last minutes, I will mention the connection to the minimal string. Okay, so the minimal string is a combination of P, Q minimal model with Liouville and ghosts. If you go to the conformal gauge, we will focus on the one matrix series 2, P because they are dual to the one matrix model. And I will use the usual notation for the Liouville coupling as square root of 2 over P. So when P is large, B is small. And okay, so then the theory becomes simpler. The large P limit, the point is that this theory becomes JT-gravity. And the new twist that I mentioned before is that this is the matrix should be interpreted as a holographic Hamiltonian, or as a Hamiltonian in a holographic sense. Now let me mention, so using CFT techniques, you can compute the density of states of the minimal string in the disk. So the idea is that we compute the path integral using the worldsheet CFTs with fixed boundary length. This is a particular boundary condition in the Liouville sector. And you can compute the partition function using the exact Liouville results. You can do an inverse Laplace transform, and you get this funny density of states as a function of E and P. And this determines in the minimal string the matrix potential up to the double scaling limit. And when you take the large P limit, you can check that this precisely becomes the JT-gravity density of states. So because both theories are dual to a matrix integral and they both share the same density of states at leading order, and that determines the theory completely, we can argue that at least to all orders in perturbation theory, these two theories are equivalent. A second way to see this is from the string equation. So the string equation is another way to describe a matrix integral that relates the partition function to a function u of x, and all the observables are controlled by this function u of x. And this u of x in the minimal string is given by this hypersymmetric function. So this is the information here is completely equivalent to the information in the minimal string. The density of states. And you can see that if you take large P, this becomes this function, which is the string equation of JT-gravity. So I can give you a sketch of a proof. We can describe the minimal string as Liouville field phi coupled to the minimal model, where the minimal model we describe in a Coulomb gas formalism as a time like Liouville field chi. And now you can define a new metric in this way and a dilaton by these field redefinitions. So in the minimal string, this factor will have a phi here, a Liouville field, but instead what we call the metric will have this rho, which is this linear combination of the Liouville field and the minimal model Coulomb gas field chi. So it's a field redefinition of these two fields. And if you plug this in the action, you will get precisely this form. So you can see that the minimal string is equivalent to a dilaton-gravity with this funny dilaton potential as well. And if you take the large P limit, you can check that this becomes this becomes a linear dilaton potential. And this is a proof, if you want, of the duality between the fact that the minimal string is equivalent to JT-gravity. And the reason why I write sketch here is because the identification of the minimal model with the time-like Liouville is not something that, to my understanding, is completely worked out in all detail. But okay, I guess this gives a good intuition of how this works. Okay, so the question on the last part is that so we have these theories with more general dilaton potential.
Excuse me, may I ask about the previous transparency?
Yeah.
So it's just a coefficient, yes? It means that the curvature is fixed by this specific negative value, which depends on p, yes?
Here.
Yes. If you integrate over phi, it's again just I don't understand. This p is just a number, yes?
Yeah, it's the p of the 2 comma p.
It's the order of this minimal model, but this section seems to be like you have no. It's just r equals to minus this 2 pi sinh pi.
Well, you cannot quite integrate out the dilaton. So what you're saying is on the equation of motion.
Sorry, I don't hear you well. There is something with the connection.
Yeah, what they are saying is on shell, or like if we look at the equation of motions, but because the dilaton is not linear anymore, this is not linear in the dilaton, you cannot exactly integrate it out.
So you mean phi is under sinh?
Phi is under, I don't understand. Phi, it's linear in phi or not?
No, sorry, phi is inside the sinh.
Yeah. I was surprised.
Yeah, okay, sorry.
So it's a specific potential, of course.
So there are two things.
I remember it, yes.
Yeah, there are two things you can say. One is at large p, this is linear, and then it's fine. Sorry about that. Okay. And the second thing that you can say is that the 2 comma p minimal model, minimal string for any value of p is dual to a dilaton gravity with this particular potential.
Yeah, no problem.
Yeah, okay. Yeah, sorry, I should have put the parentheses. Okay. So was there any question? There was someone else. I didn't. Okay, well. Yeah, okay, so in the last couple of minutes, I just want to mention what deformation of the minimal string gives you this deformation of Jackiw-Gravity with defects. So what we want to, so I went over a little fast, but this is the string equation of Jackiw-Gravity with defects. So we want some model that has a string equation that becomes this at large p. And the answer that we proposed in this paper was to consider these deformations of the minimal string. So this O of 1 comma n is a matrix model primary operator labeled by a single integer because it's a 2 comma p. N goes from 1 to, I don't know, p over p minus 1, something like that. And this is the Liouville dressing to make it a good operator to integrate. So it has dimension 1 comma 1. And these tau are the couplings of these deformations. And if you look at the dilaton gravity description with this field redefinition, this correction becomes precisely these exponential terms in the dilaton. And here I didn't write the details, but the point is, first you write this operator in the Coulomb gas representation as an exponential of chi. And then you combine this Coulomb field with the Liouville field, and you do the field redefinition again, and you will get this thing exponential in the dilaton. And this is precisely of the form of the defect that I wrote before. If you replace n times b squared by this formula in terms of alpha. So this should already tell you that this deformation should be the same as JT with defects in some limit. Or if you want to work at finite p, it will tell you that it's this funny potential with the sinh plus exponentials. To give you some intuition, so this parameter n goes from 1 to, well, p minus 1, sorry, m, p is to m minus 1. Okay, imagine that there is a P here. So at finite P, you have, because this n is integer, you have a discrete set of angles, alpha, that they are separated roughly by 1 over P, because B squared is 2 over P. This whole thing has to be an integer, so there's a discrete set of alphas. But when you take P to infinity, this discrete set becomes a continuous from 0 to 1. And alpha equals 1 will correspond to the identity operator. So this is a simple shift of the cosmological constant, if you look at it here. And this corresponds to the fact that if you add defects with 0 deficit angle, you should recover the same theory that you started with. So that's the minimal string version of it.
Sorry, can you remind, please, what is the central charge and what it becomes in your limit?
Yeah, the central charge is the central charge of the minimal model when you take large P goes to minus infinity. And the central charge of the Liouville field goes to plus infinity. So the sum is minus 26 or whatever. Yeah, so the matrix, minimal model is non-unitary series. The central charge goes to minus infinity.
Okay.
So B, sorry, I'm using the usual Liouville notation. So B is this Liouville parameter that goes to 0, and this is the semi-classical limit of Liouville, which means that the central charge of Liouville goes to plus infinity. Does it answer your question?
Yeah, thanks.
Okay. Okay, and here I draw a picture of what defects corresponds to each tachyon in this theory. And the one with the highest label n corresponds to a cusp in the JT limit because it has alpha equals 0. So the question that we want to ask is, if you have this deformed minimal string, can you solve it exactly? Is there a string equation? Namely, can you find these KdV couplings or the string equation as a function of the cosmological constant and these couplings tau? And the answer is yes. And there is a bootstrap approach in a way that was started by Moore, Cyber, and Staudacher in 91 and was almost finished by Belavin in a very nice paper of Belavin and Samolochikov. And the answer is that the string equation of JT with defects when n is large enough is very simple. You take the undeformed one, the minimal string one, and then you add something linear in the couplings, and these are Legendre polynomials, where the order depends on the minimal model label. So this is a form, I mean, okay, I'm not explaining all of it, but just there is an exact answer for the minimal model dual to this theory, and it's surprising that this is exactly linear. I think that's very surprising in tau. Because well, yeah. Okay, the idea is that we can take the string equation of this deformed minimal string as a function of the couplings and take the large P limit, and these Legendre polynomials become exactly the string equation of JT gravity with defects. And this is valid only in the range that alpha is between 0 and 1/2 from JT gravity. And from the minimal string, the reason is that when alpha is bigger than 1/2 or when n is small, then this solution of Belavin and Samolochikov is not linear in tau anymore, and there are higher order terms. And this is the exact answer, so it's kind of a mess. So I'm just showing it to you to show you that there is an answer, but you don't have to pay attention to all the details. So here P is 2n-1, kappa is related to the bulk cosmological constant of the minimal string, UMS is related to U in this way, and lambda is proportional to tau. And the prefactor here is something called the leg factor. Well, Belavin and Samolochikov calls it the leg factor, which is like the minimal string version of the leg pole factor in S equals 1, if you want. And here you can see that you have a sum over L, and different values of L come with different values of the coupling. And for each L, you have some Legendre polynomial that, okay, it is what it is. And this is the string equation that completely determines the density of eigenvalues and the matrix potential up to the scaling limit in these models. And the special property of this is that when the sum over these ni's of when you have several of these deformations is smaller than some bound, then only the term with 1 power of the coupling survives. And that's what I wrote before. But if n is very small, then you can, if n is small, then you have to sum over L and you have higher order terms. Yeah. And the nice thing is that you can take the large P limit of this formula and obtain a solution to the gravity with generic defects with alpha close to 1. And this works when the prescription of SSS cannot be implemented. So that's interesting because it gives us a different way to do calculations. And here I'm showing as an example the case with 1 generic defect. So here you see, this is the, this is the string equation of pure JT gravity. L equals 1 is the term that I wrote before. And you can see here that you have a sum over different values of L that go from 1 to this ugly combination 1 over 1 minus alpha, the closest integer to this. So it's very non-analytic in alpha. So if alpha is smaller than 1/2, this is 1. If alpha is between 1/2 and 1, this maximum power goes from 1 to infinity. And here you have some Bessel function. That's just just what it is. And this combination is interesting because this is the defect parameter of merging L of these defects. So if alpha is bigger than 1/2, these defects can merge, and you can interpret this nonlinearity as the merging of these defects. And some non-trivial check is that when alpha is goes to 1 and this sum becomes infinite, this whole thing gives you back JT again. And this makes sense because a gas of no defects should be the same as having no defects. So, and from the perspective of the minimal string, alpha equals 1 corresponds to inserting the identity that, as I said before, is just a shift in the cosmological constant. Okay, and I think this is the last slide with equations. So in the paper with Usatiuk and Weng, we found a nice way to, and also it's also being studied by Timothy Ball. There is some nice way of writing the exact, so what I showed before looks a little ugly, but you can write the density of states exactly in this way. That depends on this function W of Y, which is this correction to the dilaton potential from the defects. And this Y is a variable that you need to integrate, and this contour is the one that corresponds to an inverse Laplace transform. So it's along an imaginary axis with some, in a way that all the singularities are to the left, let's say. And the interesting thing about this formula is that by using defects with alpha close to 1, we can model more general dilaton potentials where maybe you have a huge region in the bulk with a dilaton of phi squared, with dilaton potential phi squared. And then this is regulated in the boundary by an asymptotically ADS region. But by the fact that if you go very close to the boundary, at some point, the JT term always dominates, even if alpha is close to 1. So in this way, there are a lot of questions that remain, but this is at least a starting point to try to analyze these more general dilaton potentials better. And something nice about this formula is that it matches with the semi-classical limit. So if you take, you can compute this density of states semi-classically, and this exact formula matches with that. So that's good. And I'm saying it because if you take the formula for alpha smaller than 1/2 and just analytically continue without taking into account that the solution is not valid for alpha close to 1, then you will get something that it does not have a good semi-classical limit. But okay, there is some puzzle that I don't have time to mention, but you can ask me if you want to. Okay, so that's all. So we solved pure 2D dilaton-gravity. We argue that all these theories are dual to matrix integrals, and this can be also generalized. You can add gauge fields, you can do non-orientable surfaces, you can add supersymmetry, and they're all interesting generalizations. I pointed out the connection to the minimal string, and there are some open questions, but maybe I will just stop here because it's super late. Okay, thank you very much for the attention and for all the good questions.
Thank you, Joaquin. You are very good this time, actually. So let's unmute ourselves and thanks, Joaquin. And now we have time for a few questions, comments, please.
Joaquin, my traditional question, which I asked you many times, but maybe it's worth discussing it. If I want to go to the limit of zero curvature, what should I do in your formula, and why it is difficult to do?
Yeah,
This one
yeah.
here.
So when we got this formula, I was hoping that I would be able to answer your question. But
can you
problem,
pinpoint the problem here, analytic problem?
yeah. So the problem is that the problem is the contour. What is the contour that you pick? And when W has this form, all the singularities are in a finite region of the y-plane, and then you can pick a good contour where they are all to the left, and it's consistent with the solution of the theory. But the problem is that if you put W some polynomial, some power, I get some branch cuts that go to infinity in the wrong direction that make this integral ambiguous. So maybe I should have drawn a picture, but I don't know if that was, at least you get an idea of.
But it should be hidden somewhere in this formula, this answer, yes? Why I'm interested in it, just to explain to those who are listening to us, because in this paper which you have in the resolved questions, we solved this kind of model directly, that you have flat surface with a few defects, sort of positive curvature defects, and we know what is the continuous limit of this surface. So the idea was to compare it, but I'm really puzzled. You have the analytic answer and there is nothing to compare with, but I understand.
The problem is also that, if I understand correctly, in your paper, you were doing closed surfaces, right? And maybe
we can do also open boundary.
Okay, but I thought, I don't know, maybe I misunderstood, but
no, actually in the paper, in the second of these three papers, we have actually the answer for so-called almost flat surface. There is the boundary as well.
Yeah. Okay, I see.
So maybe
I should try to compare it. It's just that, so this becomes a little ambiguous in the sense of, so I have this branch cut, so do you include it or not? And this is not that easy to integrate, so it's like, but I guess one could try to just guess which contour or which prescription for the contour, if there is any that reproduces your answers, that would be great. Yeah.
There is a finite number of possibilities here, in fact, yes.
Yeah, probably is whether you include the contribution from the branch cut or not, or something like that.
Interesting.
But so the progress compared to the last time we talked about this was that we didn't have this formula. So if you look at this one, it's kind of ugly, right? You have this lambda, but it doesn't really depend on the right combination of parameters. But this one depends only on these guys. So then you can put this function to be whatever you want, and okay.
But I don't understand, what is the limit? What should be the limit of flat space? All alphas go to 1. This is something wrong. Yes, I want to leave a few defects.
So the limit of flat space would be to replace this whole thing by y cubed. I think.
Really?
So
Why?
you can think this y squared. So this y squared is, so okay, this is related to also a puzzle that we have, which is how this is related in detail to the dilaton potential that we mentioned in the paper.
Mm-hmm.
So from the JT perspective, you would say that this W of y is the dilaton potential, and that's it, right? But now, if you use the minima string and you use this time like, so there was a paper of Samolochikov where he studies this time like Liouville and tries to relate it as much as he can to, I think he calls generalized minimal models. And so I can use that and just plug it here in this formula when I do the when I do this derivation of the dilaton potential and get exactly this normalization here. How?
Mm-hmm.
Okay, yeah. So the upshot of that, where is it? Yeah, is that this W should be interpreted not as the potential but as the pre-potential, which is the integral of the potential.
Mm-hmm.
And then this formula makes more sense because this y squared becomes a JT term because the pre-potential of a linear dilaton potential is squared. And this W and this whole thing is just the pre-potential. This y squared minus W is the pre-potential. And then if you want to do flat space and you want to put like a quadratic dilaton potential, then the pre-potential is cubic. Here the y cubed. Yeah.
Mm-hmm.
Yeah.
I see.
And then you have these funny branch cuts. Yeah. But the puzzle is why the time like Liouville normalization doesn't match with the JT one, and that I don't understand. And that was also mentioned in the Witten paper in a different way. Yeah. And I think it's an open question. Yeah. So my answer to you would be different depending on how do you identify this W with the dilaton potential. That's why. Yeah.
But the best guess is that it will be y cube. Yes.
At least it seems natural that you have this y squared always there. So it's like a JT contribution. So it's quadratic. So it's the. So I like the time like Liouville normalization. Like I like what the minima string tells me, but I don't know how to derive it from the JT perspective.
I see. Okay.